Alright, trailing zeros problem. Your task is to calculate the number of trailing zeros in the factorial n factorial. For example, 20 factorial equals to this number over here, and it has 4 trailing zeros, which we can see it is true. We have 1, 2, 3, 4 zeros at the end of this number, okay? And the input is the integer n essentially, and then we have to output the number of trailing zeros in n factorial. And n goes up to 1 billion, so 10 to the power of 9. And for the sample example here, we have the example which is described over here, okay? So for n being equal to 20, the answer is 4. So a naive solution here, which is always going to be correct, but will not make it through this time limit here of 1 second, is to actually calculate the n factorial number, and then just simply count how many zeros we have at the end of the number, right? So that will take, this solution will have a linear complexity, O(n) complexity essentially, okay? But with n being up until 1 billion, we're not gonna pass the time limit here. For the C++, this is even harder because we're not going to be able to use our data types. We're gonna have to implement the numbers in strings to be able to contain n factorial, because 1 billion factorial is a huge number essentially. Yeah, so this solution is not good for the time limit, and implementation wise it's even hard. You can avoid this implementation hardness by using Python, but still again you will have this time limit, okay? So we have to question if there is a solution which achieves such a complexity that for an n that reaches up to 1 billion, it will manage to give a solution below this time limit, okay? And there is a solution, and to identify that, we need to change the question, the question we have here. So instead of counting the trailing zeros of our number, what we should focus on, how we can rephrase this question, is actually to count how many times our number is divided by 10, okay? So now let's go ahead and look into the math of this and see how we can find a solution which has such complexity that for n reaching this huge value is able to achieve a solution, an execution time below 1 second. Alright, so if we write down 10, okay, and its prime factorization, 10 equals to 2 times 5 essentially, okay? So if we were to calculate n factorial, which is equal to 1 times 2 times 3 up until n, okay, for those that don't know, if we get, instead of calculating this number, okay, which would actually need n steps to do so, we can just, we're gonna need its prime factorization. And since 10 equals to 2 times 5, the only thing we need from this number's prime factorization is the powers of 2 and the powers of 5 in n factorial's prime factorization. So n factorial's prime factorization would be 2, okay, to some power x times 5, okay, to some power y, times some other numbers here for which we don't care about. The only numbers we care about is 2 and 5, okay? And since 2 appears to, is a smaller number than 5, so it appears more frequently in prime factorizations of numbers that we have in the range between 1 and n, we know for sure that x will be actually greater than y, okay? So the only thing left to do is to get the smallest of these two values, so y essentially, okay? So the only value you care here is y. So what is the power of 5 in n factorial's prime factorization, okay? So the problem immediately becomes easier now, okay? Just by seeking for this number y, we can answer the initial question of the trailing zeros, because as many times as 10 divides n factorial, that's the amount of trailing zeros we will have in our number, okay? So 10 to the power of y, essentially, which is the number that we're going to find here, will for sure divide n factorial, okay? So this n factorial divided by 10 to the power of y will result into an integer number. And that, in that way, number y here is the answer that we seek, okay? So let's go now ahead and see how can we actually calculate this number y. So to calculate this number y here, what we need to do is for every individual power of 5, so 5 to the power of 1, 5 to the power of 2, up until 5 to the power of log base 5 of n, okay? For every such power of 5, we need to calculate how many times that power appears in prime factorizations of numbers between 1 and n, essentially. So if we were to write down the first numbers, which are have 5 in their prime factorizations, so 5, 10, 15, 20 here, 25, and I'm just gonna skip ahead for until 125 here, to just for the sake of the example here. Here we're gonna have 5 to the power of 3 as well, okay? So for the sake of the example here, let's just write down only the 5s in the prime factorization of these numbers, okay? So here we have 5, just one 5 again, just one 5, just one. So here we're going to have two 5s. So 25 actually is the square, 5 squared essentially, okay? And 125 is 5 times 5 times 5, okay? So 5 to the power of 1 appears in all of these numbers, okay? 5 to the power of 2 appears to 25 and 125. And 5 to the power of 3, okay, appears only in 125. But if we keep writing numbers, for example, let's say 4 times 125, okay, that will give us 500 essentially, okay. So 4, we just write this here in another column here. So 4 times 125. This equals to 500 essentially. So for 500, the prime factorization goes 2 squared times 5, 5 to the power of 3, okay? So 2 squared times 5 times 5 times 5. So even for this number, we're gonna calculate for every single power its appearance. So 5 to the power of 1 appears in this number, 5 to the power of 2 appears in this number, and 5 to the power of 3 appears in this number. So by calculating all of these, okay, appearances for every single power of 5, we will end up, if we look at these like columns here, okay, we will end up counting essentially how many times 5 appears in the prime factorization of all of the numbers, right? So if we had an array here, so occurrences of some power, okay, so for the first power of 5, and then we would have the occurrences of 5 to the power of 2, and then the occurrences of 5 to the power of 3. In all of these, in all of the numbers in this range, in all of the prime factorizations of numbers in this range, we will simply just add these values. So add these values of this array, and that will give us actually number y, okay, which is what we are searching for. So let's go ahead and see how I implemented this solution. All right, so initially I'm just reading number n here. I set the answer to be 0. And then with this while loop here, we will count the occurrences, how many 5s we have in the prime factorization of n factorial, essentially, okay? So we begin with the first power of 5. So this p5 stands for power of 5. So 5 to the power of 1, okay? And up until the power of 5 that we're looking at is smaller or equal to n, we will execute the following. So the answer, we will append to the answer, okay, the occurrences of that power in the range from 1 until n. And how we do that is knowing that we have n numbers essentially, and that every p5 numbers that the power will be appearing. So for 5, for example, every fifth number will actually have 5 to the power of 1 as part of its factorial, okay? And for 25, every 25th number will be divided by 25, and thus 5 to the power of 2 will appear in its number, in its prime factorization, okay? So we simply divide n, okay, with p5, okay, every time. And we append this to the answer. And then we have, we multiply by 5, okay? So p5 is multiplied by 5 every time, so that we jump to the next power. And then we just simply output the answer at the end, which will have the accumulated number of 5s in the prime factorization of n factorial. And that will lead essentially to finding out how many times the power of, how many times the number is divided by 10 essentially, okay? Just as we have shown based on the prime, on the prime factorizations, okay? So if this video helped you solving this problem, if you got stuck in the process of finding out this solution here, please leave it a like, subscribe to the channel, and I will see you in the next one.